77 shows a circuit like this here and asks a couple of questions here. In particular, it says that if this switch has been closed for a very, very long time, what must be the charge on the capacitor? So there's a bit of logic you have to think about for problems like this. Just don't start attacking it necessarily right away. But if this switch was closed like this, then what you get here is sort of a current loop this way. There'll definitely be current coming out of this battery here and sort of ends or dies at the junction right there. We can call it I1 if you want. And we're not necessarily going to use Kirchhoff's law for this. I'm just trying to illustrate where the currents are, what the currents are doing. And when it comes to the junction, another current is definitely going to go down through this resistor and indeed go all the way back up to the battery. But we have to call it I2 because we don't know exactly how much of I1 is going to split off and come down this junction, but we have to call a different variable there. And since it is a junction, the current I3 is going to go this way, and that's the current that's going to go through the 10 ohm resistor and end up charging up the capacitor in there. So the question that they're asking then is, in part A, is what is the charge on the capacitor after the switch has been closed for a very, very long time? Well, there's a couple things you can conclude here. When you hear long time, which is sort of the key word in this thing here, what you can conclude then after a long time is that the capacitor is full. The capacitor is fully charged. Capacitors only can hold so much charge, which is given we got by Q is equal to CV. So when it's fully charged, there will be some maximum Q on it here. We know what the C is, it's 20 microfarads, and there'll be a certain voltage across the capacitor when it's full, and it'll stop. But the key thing about the capacitor being full is because it's full, it's no longer accepting charge. And what that means is this I3 here, when time gets very long, or time goes to infinity, so to speak, very long time, I3 here is going to drop to 0. Because the capacitor is no longer accepting charge. There won't be any more current traveling down here because the capacitor is full. It's saying enough of that. So what happens at very long times, it's almost like this branch of the circuit doesn't exist anymore after very long times. And so there's some things you can figure out about the circuit by doing that. So in particular here, if this branch of the circuit is gone, which it is in very long times because the capacitor is full here, what you'll have then is a 100-volt battery sort of feeding a 100 ohm resistor. And where I got the 100 from was the series combination of the 60 and the 40. Now I know you're saying the 60 and 40 are not in series the way the circuit's drawn, and I agree with that. But remember, at very, very long times, there's no more current going down this loop because the capacitor is full, so it's like this section doesn't exist anymore. So in this configuration, which only exists in very, very long times, the 60 and the 40 are in series because you don't have choices of current about where you're going to go. You come out and go through the switch and you don't travel. You can't travel down this junction because the capacitor is full. You must go down there. So they are in series. So what I get then is no matter at very, very long times, which is what the problem is calling for here, I1 is 1 amp at very, very long times, 1 amp going through. Now the reason why I need that is the following reason here, because I can figure out what the voltage must be right here at very, very long times because the 1 amp is being dropped across the 60 ohm resistor right here. So if 1 amp, if I1 here is 1 amp traveling out of the battery, then the delta V across this resistor right here, the delta V right there, is going to be something like 1 times 60 or 60 volts. That means this point right here is going to be at 40 volts. Because it comes out of the battery with a potential of 100 volts, but it drops 60 volts across this resistor. So this point right here is going to be at 40 volts. Now, the reason why I need that is because now I'm able to calculate what, say, the voltage will be across the capacitor, and here's how. If there's 40 volts at this point right here, it means there's 40 volts sort of across this leg of this 10 ohm resistor and the 20 microfarad capacitor. So I'll just sort of draw over here that if I put a voltmeter in here like this, it would read 40 volts like this and like this. So this isn't another circuit element. I'm just saying I put voltmeter probes in like this. This could be the red one right here if you want. And the black one, doesn't look like I have a black color here, but I'll just pretend it's blue there, would give me the 40 volts. Now why is that important? Because remember, when the capacitor is totally full, there's no charge going down this loop. The capacitor is full. If there's no charge or no current going down this loop, that means there's no current going through this resistor right here because the current's been shut off due to the full capacitor. That means the potential drop across this resistor is 0 because I is 0. Remember that Ohm's law says delta V is I times R across the resistor. Now if I drops to 0, then the voltage drop across the 10 is 0. That's important because if this is 40 and this voltage drop is 0 because there's no current flowing, that must mean the voltage across the capacitor is 40 volts. So this voltage right here is 40 volts. So after long times, whether I take this voltmeter probe and put it here on top of the resistor or down here right on top of the capacitor, I'm going to get 40 volts. Now it's important to me because now I can figure out how much charge is on the capacitor, which is what the problem is asking for, because Q is equal to CV. And if I know C is 20 microfarads, I know the voltage is 40 volts, I get something like 800 microvolts or some weird number like that, which I can give you a better answer on right there. Ooh, pardon me, it's not even volts, it's supposed to be coulombs in there. So 20 times 40 is about 800 microcoulombs. So that's the answer you'd sort of get for that one.